Hello, and welcome to this tutorial on the dilation. My name is Yuchen Wang. And in this tutorial, I want to show you this mathematical method called dilation that can turn a non-unitary operator or matrix into a unitary operator in a larger or higher dimensions. So let's begin. Before we move on to the mathematical form, let's use a graphical illustration to understand how a non-unitary matrix defined on a lower dimensional space can become unitary when dilated to a higher dimensional space. Here, this circle here represents a lower dimensional space that is our original space. And we're working with the quantum a unit vector on the circle that our quantum computer can handle. Because our original operator is non-unitary, so after applying it to this vector, the vector becomes shortened and no longer on the circle, which is no longer on our computational space. What the dilation do is it will increase the dimension to a unit sphere. And this dilated operator U of G can work with this blue vector on the unit sphere and is unitary. And thus we can find the blue vector that can correspond to each of this red vector that we want in our original lower dimensional space. And this is how dilation works. Next, let's talk about the unitary one dilation process. Here are the dilation. That is, after applying the dilation to our time evolution operator G prime here, we have the unitary operator UG prime. Because this UG prime are of higher dimension, we need to add this zero. This extra zeros act as ancilla to make sure the dimension of the vector matches to that of this unitary operators. And this dilation came from the SZ-Nagy dilation theorem that for any contraction G prime of a Hilbert space H, it has a corresponding unitary operator U of G prime in a larger Hilbert space. Here, the contraction means the operator norm of G prime is smaller or equal to 1. And we have the explicit mathematical form of this UG prime. And here, this D of G prime is called the defect operator of G prime, and is defined by taking the square root of identity minus G dagger G prime. Okay, next, we talk about the application of dilation. In our case, it's simulating an open quantum system dynamics. Here, our dynamics of open system is represented by the sigma t, the density matrix. And by applying the time evolution operator or the propagator G of t to the initial state sigma 0. On a quantum circuit, the sigma 0 will be our input, and we use unitary gates or quantum gates to apply these propagators, and we do the measurement to obtain or to retrieve the sigma t, which is the dynamics of our system. It's very easy to draw a one-on-one relation with the sigma t and sigma 0. However, because G of t is not unitary, we cannot build unitary gates out of it. And then we introduce a dilation, which is listed here. And we can actually use the unitary gates or quantum gates to represent this dilated unitary U of G prime. Notice that in our calculation, our propagator GT itself is not always a contraction, which means sometimes its operator norm can be larger than 1. So we need this NC, which is a normalization factor, to scale it. So our G prime is always a contraction, as you can see here. Next, after this dilation process, our originally 4x4 G prime, our propagator with a real imaginary part, we apply the dilation and it becomes an 8x8 matrix. This 8x8 matrix is our unitary U of G prime. which we can use the built-in functions to build a quantum circuit out of it. And you can see that for the 8x8 matrix, we need 3 qubits to represent. And here is an illustration of our quantum circuit. Finally, let's show you how to work with this dilation with some Python code examples. We first need to import some useful function from the SciPy or NumPy packages. This GM is our G matrix, our propagator. We use this command to calculate its operator norm. If this norm is larger than 1, which means it is not a contraction, then we divide it by our NC factor. And if this is a contraction, we just do nothing. After this, we first calculate the conjugate of our G matrix. And then we calculate the defect operator with this special function that can take a square root of a matrix. We also calculate the conjugate of that defect matrix. Finally, we use this np.block command to combine these 4 blocks into a 1 matrices, which is our unitary U of G prime. And this marks to the end of this tutorial, and thank you for your listening.